Okay, so hello grade 8 students. What we're going to do now is we're going to try to prove the formula for finding the number of diagonals for a given polygon. Okay, so the formula for finding the number of polygons for finding the number of diagonal for a given polygon is given by the formula. So we have here d sub b. Okay, so we have here d sub b, so it's the number of diagonals for a given polygon is equal to n times multiplied by n minus 3 quantity n minus 3 all over 2. Okay, so the first thing that we have to do for this kind of proof is we have to use mathematical induction. So what does mathematical induction mean? It means that from the word induction, induce, you have to add a certain number or a certain value in order to prove the thing that you want to prove. But for this one, we want to prove this formula. Okay, because the geometers, the great mathematicians, didn't just come up with this formula out of nowhere. They didn't just come up with, oh, here's the formula for the diagonals. Oh, hooray. Okay, so no, they had to really prove that formula. So in order to prove this formula, we're going to use the mathematical induction of proving. So the first step is, of course, the base step. So what do we do with the base step? In the base step, we have to prove that for this formula, it's true for n. So as n is the number of your sides, n is greater than or equal to 3. So why 3? Because a polygon starts with 3 sides, of course, and 3 angles. Okay, so there. So it always starts with 3. Okay, n should be greater than or equal to 3. The value of n should be greater than or equal to 3. And the value of our diagonal here is has to be 0. So why 0? Because a triangle cannot have a diagonal. Okay, so this is not a diagonal because this is not a vertex. Okay, that's just a point that we wrote there. Okay, so that means the diagonal of a triangle is 0. Okay, so let's try to use that. Let's try to prove that using the formula that we have here. So we have there n times n minus 3. So that's going to be n. What's the value for n? If it's 3, so that's going to be 3 times 3 minus 3 all over 2. And what's 3 minus 3? That's simply 0 times 3 all over 2. So you get, so 3 times 0 divided by 2. So that's 0 divided by 2 and you get 0. Okay, so this is the number of diagonals for a triangle. So how about for a square or a quadrilateral? So for a quadrilateral has, for example, this is a quadrilateral. So it has 2 diagonals. Okay, so let's try to use this formula to find the number of diagonals for a quadrilateral. Okay, so we have here, what's the value of our n? So that's 4. Yes, that's a quadrilateral. That's the number of sides it has. So 4 times 4 minus 3 all over 2. Okay, so what's 4 minus 3? That's simply 1 times 4 all over 2. So that's going to be 4 over 2, and 4 over 2 is simply 2. And therefore, we proved the number of diagonals for number 2. Okay, so how about 3? Maybe we can extend to 3. Is it still true for number 3 for the third polygon that we have? So that third polygon would be the pentagon. Okay, so a pentagon has 5 sides. So let's try to substitute this value, the number 5, the number of sides for this formula. So we have there 5 times 5 minus 3 all over 2. Okay, so all over that. So 5 minus 3, so that's simply 2 times 5. Okay, times 5 times 5, that's going to be 10. And 10 divided by 2 is going to be 5. So there are 5 diagonals for a 5-sided figure or a pentagon. So if you want to prove that geometrically, if you want to draw a figure, so let's draw here a pentagon. Okay, so this is a pentagon, and let's try drawing some diagonals. So this is a diagonal, so that's one diagonal. There's another diagonal, so that's the second diagonal. And we also have a third diagonal right here. There you go. And then we also have a fourth diagonal right here. And also we have a fifth diagonal right here. So we kind of like form a star. Okay, and there you go. You have 5 diagonals for a pentagon. And that's also what we get for our base step. So this is our base steps, huh? Okay, so this is the base steps for our problem. So we try to substitute values. But after the base step comes the induction step. The induction step simply means, does this still hold true? So does this formula still hold true after 5, 6, 7, 8, 9, and so on and so forth? So how do we prove that? We use the induction step using mathematical induction. Okay, for the induction step, we have here n. So again, n is the number of your sides. So let's write that down. N is the number of sides. Okay, so if n is the number of sides, we have to equate that to k. So n is equal to k. K is some constant that we have here for our mathematical induction proof. Okay, and of course, since n should be greater than or equal to 3, then k should also be greater than or equal to 3. So this follows that since our formula d sub p, the diagonals for a given polygon is n times n minus 3, n times n minus 3 all over 2. So that's going to be for k, d sub k is equals to k times k minus 3 all over 2. Okay, because we now use the constant k. So this is how we do it in mathematical induction. Okay, since it is true for n, it also follows that n plus 1 is also equal to k plus 1. Okay, so that's given by the formula right here. Okay, so we have here n plus 1 is equal to k plus 1. So what we're going to do here is we see this formula. This is the new formula that we have for the mathematical induction. D sub k is equal to k times k minus 3 all over 2. So what we're going to do here is we're going to try to replace k with n plus 1. Okay, since this is induction, what induction literally means is you have to add a certain value in order to prove that the certain value is true for all of the values that will follow. So we want to prove that it is true for n is greater than or equal to 3. So that means it's true for 3, 4, 5, 6, 7, 8 until infinity. Okay, so that's what we want to prove. Okay, so here we have n plus 1 is equal to k plus 1. So if we substitute that to the value of k, the value of n plus 1 here, which is k plus 1, we get d sub k is equal to k plus 1 times k plus 1. Okay, let's write that neatly. So k plus 1 minus 3 all over 2. Okay, so we have that formula right there, and I think we can simplify that a bit better. So that's going to be k plus 1 all over 2 times k minus 2. Okay, so this is the formula for d sub k. This is what we want to prove. Okay, so how do we prove this value? Okay, so remember, we want to prove this value. This is going to be our RHS. So what's RHS? That means that's going to be the right hand side of our formula. So we have the right hand side and then we have the left hand side. So what we're going to work on is the left hand side. That's how we are trying to, that's the strategy. We first have to settle the right hand side, and we've already settled it. The right hand side is equal to k plus 1 all over 2 times k minus 2. Then we have to prove the left hand side, and that's what we're going to do for our next topic. Okay guys, so to prove the left hand side, this is what we're going to do. We're gonna try to look for a pattern. Okay, so you see the polygons right here, guys. Okay, so we have here a polygon. So we have here, so this is the number of sides for the polygon. So we have 3, so that's a triangle, 4 a quadrilateral, 5 a pentagon, 6 a hexagon, 7 a heptagon, 8 an octagon, 9 a nonagon or an enneagon. Okay, so on and so forth. Okay, and then we have the number of diagonals that it has. So we're going to try to find a pattern. Okay, so the number of diagonals that a triangle has is of course 0, because that's 3 times 3 minus 3 all over 2. So that's going to be 0 divided by 2, and that's going to be simply 0. And then for a four-sided figure, for a quadrilateral, it has 2, it has 2 diagonals. For a pentagon, so for a 5-sided figure, it has 5 diagonals. For a hexagon, it has 9 diagonals. Okay, so how do you compute that? Again, for example, it's 6, so that's going to be 6 times 6 minus 3 all over 2, because the formula is n times n minus 3 all over 2, so that's going to be 6 minus 3 is 6 minus 3 is 3, and 3 times 6 is 18, and 18 divided by 2 is simply 9. Okay, so for 7, we have there, so let's say for example 7 minus 3, so that's going to be 4. Okay, so let's try to solve for the value of 7, so that's going to be 7 times 7 minus 3 all over 2. Okay, so that's going to be 7 minus 3 is simply 4, and 4 times 7 is simply 28, and 28 divided by 2 is 14. So that means a heptagon has 14 diagonals. And for 8, so that's going to be 8 minus 3, so that's 5. 5 times 8 is 40, and 40 divided by 2 is 20. Okay, 9, so we have here 9, and then if we substitute that to the formula, we have 9 minus 3, so that's 6, okay? And 9 times 6 is 54, and 54 divided by 2, you get 27. Okay, so the number of diagonals for an enneagon or for a nonagon is 27. Okay, so let's try to erase this figure that we have here, the values that we have here. So what we're going to do, guys, is we're going to try to find a pattern. Okay, so we're going to try to find a pattern. So the pattern here is we have here the number of sides 3, and then number of sides 4, 5, 6, 7, and then 8, and then 9. And then as the diagonal increases, we can notice that we can form a pattern of, so we can simply add per polygon. Okay, this means that there is n minus 2. Okay, we're adding n minus 2 per increase of one of the polygon. So how did we get the n minus 2 here? So we have here 4 and 2. Okay, so when you minus 4 and 2, you get 2. Okay, and 2 plus 2, okay, the answer is 4. So that means we had an additional of 2 diagonals for this figure right here, because it was 0 a while ago. And then we have here 5. Okay, so we have here 5. 5 minus 2 is simply 3. And then if we add 3, 2 plus 3, you get the diagonal 5. Okay, and then we have here 6. So 6 minus 2 is 4. Okay, and 4 plus 5, that will give you 9. Okay, and then we have here 7. 7 minus 2, okay, 7 minus 2, the sides minus 2, so that's going to be 5. And 5 minus 9, and 5 plus 9, that's going to give you 14. Okay, so the next pattern is going to be 8. Okay, so 8 minus 2, so that's going to be 6. Okay, 6, and then 14 plus 6, you get the diagonal here, which is 20. And then we have here 9. So 9 minus 2, so that's 7. Okay, 9 minus 2 is 7, and then 7 plus 20, you get 27. Okay, so now that we have our right hand side here, so the value of our right hand side is d sub k plus 1 is equal to k plus 1 all over 2 times k minus 2. Okay, so how did we get that? Again, we tried to substitute. We substituted the value of k here. So since this is an induction, so that's going to be, it's for k, so that's going to be k plus 1 all over 2. And so for this one, we have to substitute k plus 1. And then k plus 1 minus 3, okay, since that's the formula for the diagonal. So k plus 1 minus 3, you get k minus 2. Okay, so the right hand side is already good. Now we have to prove the left hand side. So how do we do that? So we have here the formula d sub k plus 1 is equal to k times k minus 3 all over 2 plus k minus 2 plus 1. So where did we get this k times k minus 3 all over 2? Again, this is the formula for the diagonal, for the number of diagonal for any polygon. and then we added 1 to that. So why did we added 1? We added 1 to it because this is an induction proof. So an induction proof means that you have to add a specific value. Normally that value would be 1 for increasing number of values to prove that for the entire set of n is greater than or equal to 3. That means that it is true for all of those values. Okay, so we have, that's why we added a 1 there. And we also added a k minus 2. This is the one that we proved a while ago from the pattern that we discovered. Okay, so we discovered that from n minus 2, there's going to be an increase of diagonals per increase of number of sides of the polygon in n minus 2, in an n minus 2 term. Okay, so from, for example, again, so if you have a quadrilateral that has 4 sides, so you need to add 2 to that to get the number of diagonals. So 0 plus 2, so there's 2 diagonals there. And then you need to add 5 minus 2, so that's for the pentagon. 5 minus 2, so you're gonna get a 3, and 3 plus 2, you get a 5. Okay, so the pattern continues, and the pattern there is n minus 2. Okay, so how do we solve for this algebraic expression that we have here? Okay, so what we have here is k times k minus 3 all over 2 plus k minus 2 plus 1. So what we do here is we add the 1 here, so that's going to be d sub k sub 1, k plus 1 is equal to k times k minus 3 all over 2. And what's k minus 2 plus 1? So that's simply plus k minus 1. Okay, so what we're going to do here is we have to multiply this term by 2. Okay, so this means this cancels out, and what we're left here is with d sub k plus 1 is equal to k times k minus 3, okay, plus 2k minus 1. Okay, so since we added that, there's still an over 2 over there for the entire term since we added that. Okay, so the next thing that we have to do is we have to multiply those. So we get k squared minus 3k and then 2k. So we multiply that 2 times k, so that's going to be 2k, and then 2 times negative 1, so that's going to be negative 2 all over 2. Okay, so what we have here is we can simplify this. So we have k squared and negative 3k plus 2k, so that's simply minus k or negative k, and then minus 2 all over 2. And then this is a trinomial, k squared minus k minus 2. We can try to factor this trinomial. Okay, so the factor of this trinomial, so we have here, so let's try to follow. So d sub k plus 1 is equal to, so the factor of k squared minus k minus 2 all over 2, so that's going to be k minus 1 multiplied by k minus 2. Okay, and since that's all over 2, we can divide that by 2. And there you go. Okay. Okay, so we have to factor k squared minus k minus 2 all over 2. And the factor of that is going to be k plus 1 multiplied by k minus 2 all over 2. And there you go. That's how we got the answer right here. So this is the left hand side. Okay, so this is the formula. K plus 1 all over 2 multiplied by k minus 2. And we also proved that equal to the right hand side. So the right hand side is also k plus 1 all over 2 times k minus 2. And therefore, they are the same. And therefore, this formula holds true for n, for k, such that k is greater than or equal to 3. And since k is equal to n, then it also holds for n is greater than or equal to 3. So that's how we prove by mathematical induction. You have to, the right hand side of the formula has to be equal with the left hand side. With a bit of imagination, we can try to solve this problem.